All right.
Yeah.
All right, go ahead, Jackie.
Well, thank
Welcome,
you for,
welcome. Oh, we're so grateful for um, Will coming back, and he has been with us for the past 2 years. This is such an awesome opportunity. We want to welcome Will, and his subject matter, computer science, is the study of algorithmic processes, computational machines, and computation itself. So we welcome Will, and he is an assistant professor at the University of Cincinnati. Thank you,
the
Will,
other
for
you.
joining us. And
Yeah,
I'll
thank you
hand
for
you the
having
mic.
me. Thank
You
you.
have the mic.
Thank you. So great to be here. Yeah, we're the other UC. So on the East Coast, if you say UC, or in the Midwest, if you say UC, you get us. And if you say UC anywhere else, you get the entire system of California schools. So
Yes, you do.
yeah, we have a lot to live up to. So um, well, thanks again for having me. And so what I want to do tonight is I want to tell you a little bit about what it's like to be a computer scientist. And I have something really cool cooked up tonight that I've never shown before. And so I think you're really going to like it. So I'm pretty excited about it. I'm going to share my screen so I can show you this presentation. And then we're going to do our demo here. And I think you're really going to like this demo. So let us start here. All right. So I want to talk to you a little bit tonight about who a computer scientist is, who can be one, and what does that mean? So I just want to start with all the people in my life who I know that are computer scientists and how different they all are from one another. Now, you may not, I may not know this person because look at her, look how well respected she is. She's off somewhere in the military, and I don't even stand a chance next to her. But she is one of the most famous computer scientists in all the world. She was the first person to come up with and implement the idea of a programming language that is more than just at the machinery level. Like, she gave us things like more natural programming languages that we can use. And I think that's so cool. And that's just one of the people on this list. These are all other people that I've worked with in the past. And what I want you to really take home with you is that anybody, absolutely anybody, is a computer scientist. And I think that's amazing. I think that's what is one of the great things about computer science, is that anybody can do it. All right. So what does it take to be a computer scientist? What does it mean to be a computer scientist? And I think it was Miss Pringle, if I'm not mistaken. I think that's who was introduced me. She gave me a great introduction. Is that right? Did I get it right?
Yes, it is.
But okay, good. All right. I wanted to make sure. She gave me a great introduction. She gave us such a great definition of what it means to be a computer scientist. And here is my take on what it is to be a computer scientist. I said that a computer scientist is anyone who solves problems using a computer. That's all it is. And just think about all the different problems in the world that we can come up with. And we're not talking about like bad problems, like, oh no, these are problems. No, these are fun. Like, these can be fun and positive problems. Like, how do I make things easier? These aren't like, this doesn't have a negative connotation. These problems are fun. These are positive problems. These are a way to make us all better. And I think that's what's so cool, is that we can take all of these challenges, and even challenges that we don't see, and we can make things better for people around us. That's what I love. I love being able to make things that help other people live their lives better using a computer. And that's what I do. And I think that's what it means to be a computer scientist. And like I just said, the best part of being a computer scientist is just solving problems using a computer. It's such a challenging thing to do, too. You're never bored, because every different problem that you come up with has its own set of little challenges and things that you have to learn. You're never done learning. I'm a very curious person, and I love the fact that being a computer scientist means that I have to be curious every day and that I can never not be curious anymore. So that's what I love about it. I don't know. I think, who did we have? Did I see Keenan on saying that or Nitu, that he came on? Did I see him? So I didn't know if excuse me, if Nitu had any experience with computers, but I was wondering if they did, maybe they would want to share what they liked about playing with computers. Excuse me, I've got a cough. We'll give him a second to, if he wants to, if Nitu wants to respond, we'll. All right. All right. We'll assume Nitu is shy, so that's okay. All right.
I got something in the chat.
Oh, great.
Okay.
Yes, that's awesome. I like working with code and seeing what can go. That's exactly right. That's exactly right. It's so cool, right? Who said something about Fortran? Was that Victor?
Oh yeah, no. When you were talking about the older lady, and you were saying that she made computer language easier or more accessible. I was thinking that Fortran probably wasn't one of those ones.
It's funny because it actually, that was one of the early ones, but she invented something called COBOL, which is very similar to that. So,
I didn't know that.
Yeah, isn't that cool?
Nice. Because I've heard of COBOL, but I've never actually seen what the code looks like for COBOL or Fortran. But I know that I've had people who have been around for like 30, 40 years, and they've been exposed to it. And well, maybe older than that. And that they were talking about how Fortran was very difficult to understand. It was user friendly.
Yeah. It's funny though, because what's so fascinating about those two languages is two things. One, they were invented in the middle of the last century, like in the 60s, in the 1960s, and they are still very, very, very popular languages today.
Really?
Yes, during the pandemic, there was a huge spike in demand for COBOL programmers because all the systems, the COBOL stands for Common Business Object or Business Oriented Language. And so all the business applications that the governments use to process payments, to process stimulus checks, to process payrolls, those are all written in COBOL. And so as the programmers retire who know COBOL, we need people to maintain that code. And so we are trying to actively recruit people to use that, to learn that language so they can keep our systems up. It's amazing. It is absolutely amazing. Yes. I think it's so cool.
That is really interesting.
Isn't it awesome? I just think it's like,
I'm just thinking like, because I mean, I would think that the government would use things that really work. Like I was talking to this guy and he's in robotics, and a lot of people still use the fax machine because it's secure. And a lot of government organizations still use a fax machine because they're concerned about physical cyber systems, and that they don't have enough implementation for cybersecurity right now, and a lot of things are kind of exposed.
And that's why they still have COBOL systems, because they know they work and they don't want to change something that works. It's expensive. So this is why it's so cool. This is why it's so cool. And I love Mary's answer. Mary said, I like working with code and seeing what can go wrong. That's exactly what we do as computer scientists. We look to see what can go wrong and then we fix it. It's just a constant cat and mouse game. It's amazing. I love it. All right. So one of the things I want to talk about tonight is just what kind of problems we can solve. And I think this will go a little bit towards what Victor was just talking about all the challenges we have with cybersecurity these days. And so what I want to show you is, I'm going to make sure that this is down because we don't want to hear the volume. So we'll make sure it's muted. But this is something that I got to participate in. This was a tournament that I worked on where we got to build a robot, an artificial intelligence. This was a few years ago, an artificial intelligence that would attempt to infiltrate someone else's system, but also at the same time to defend itself against that system. And so we actually competed with a bunch of other people from around the world, and our team finished second. We won $1 million. I've told this story before. We won $1 million. And do you know how much money I won out of that $1 million?
How much?
Yeah, I'm still working, Victor. So let's put it that way. How's that sound? So let's look at this. I want to show this video because I think this is a really cool animation here. Let me just mute that audio so we don't hear it. But what I want to show you is this is what everything looked like. Our system, when it was running, looked like this. And what's happening here is these are all of these things, these images being sent. Those are packets being sent. Those are little bits of data and commands being sent to our computers trying to infiltrate us. And what you're seeing here is that these other ones that are sort of going between them, those are us attacking the other competitors as well. And so one of the things that our system did tremendously well as a result, or one of the things we worked on, our system really excelled at, was defense. We were really good at defense. We weren't so good at offense, but we were really good at defense. And so that made me happy. I thought that was a pretty cool thing to be able to say, look, we were really good at defending against other people's attacks. And that doesn't necessarily, I wasn't particularly interested in the offensive side of things, trying to break into other people's things, but defending ourselves, I thought that was really cool. And so this is the system that it looked like. This is how it looked when we were actually playing the game. And that visualization is really just so cool. So one of the other things that's really cool is one of the problems that I help my students solve in my first year programming class is this thing talking about the coronavirus. And we've now got a pretty good idea of, at the chemical level, at the biological level, what the coronavirus looks like and how it binds to different things. And we've done a sequence on it, a DNA sequence. And so one of the algorithms that you can write with this is this algorithm where you can take a bunch of different sequences of the coronavirus and you can compare them to one another and you can see if they fit together. And if they fit together really well, what that means is maybe this different type of virus, this variant of the virus, isn't going to cause as much harm. And so we might be more safe. We might be able to reopen the schools. We might be able to avoid shutting down the schools. You might be able to continue to go on your airplanes. But if there's a big difference, if there's a huge gap, then maybe it's gonna be more severe because it's gonna bypass all of our vaccines if this is something that looks so different that we've never seen before. And so one of the things you can do is we can use this little algorithm down here. An algorithm is just a series of steps that you use to solve a problem. And so we can set up a series of steps where we have different bits of the DNA going this way, laid out this way, horizontally, and we can have different bits of the DNA laid out vertically. And then we can fill in these squares inside of here with different numbers, and this will give us a score of how similar or different they are. And I know you're all going to be computer scientists when you grow up. And I also know you're going to go to the UC. You're going to go to my UC. And so when I see you as students, this is what you'll get to do. This is so cool. Absolutely the coolest thing. I think this program that we get to write is really, really neat. All right. we're going to skip this one because we've got a lot of other fun stuff I want to get to. But I want to talk a little bit more about the coronavirus. I'm sure you all remember this from a few years ago when we were really worried about what was going to happen when it first came to the United States. We were worried about this initial peak of how many people we were going to have to worry about protecting and making sure that we had enough capacity in our hospitals to keep people safe. And one of the things that computer scientists did with the medical professionals, is to try to use the medical professionals' understanding of how people transmit viruses to one another, how they breathe, when they bump into each other, how far did their air go? And one of the things they did was they can make estimates for how many people are going to get sick at what time. And so what I was able to do was do a little example of this. And what you see on the left is this little example program that I wrote that uses the models of epidemiology, which is the study of how viruses spread and how diseases get transmitted in the population, and build a model. So we were able to say, look, in a few days from now, in 9 days, we're going to start seeing the infections go up. But then they're going to hit up here and they're going to slowly start to come back down. So maybe it's going to be okay. And what you can sort of see over here, this is the actual data that was generated. This is actually what happened. So what's really cool is our people who are trying to protect us can say, look, for these next few days, we're going to have to be really safe. We're going to be really safe and stay very far away from each other because we're at high risk. And that's another kind of thing that computer scientists can help with. And what I think you'll notice, and this is what I love, is that just because you're a computer scientist doesn't mean that the only thing you have to work with are computers. I love it because I get to go out and learn other fields. I had to learn about epidemiology. I had to learn about biology to be able to do these things. And I love that kind of stuff. It gets me to think about other things and keeps me excited. All right. So I want to do this brief example, and then I'm going to show you something else, and you're going to help me with this next part. Not this part, but the next part. One of the other things that I think is really important in our world today is for people to be able to communicate with those they care about and love without having to worry about anyone else reading their messages. I want to be able to tell my mom I love her, and I don't really want anyone else to be able to know that. I mean, I would tell anybody because I just told you all, but I want to have that just between us. That was meant for her, and I just want her to be the only one to have that. And so what you can also do as a computer scientist is you can write these algorithms. There's that word again, algorithm. The steps, the series of steps we're going to use to do something, to solve a problem. That's our algorithm. And what you're going to do is you're going to build this system where every time I want to talk to my mom and I, because we know each other so well, we've come up with a secret number that we both know. Let's say it's 3. And so what I'm going to do is if I want to send her the letter Y, then what I'm going to do is instead of sending letter Y, I'm going to go 3 letters to the right in the alphabet, and I'm going to send her that one instead. So I'm going to start with Y down here, and then I'm going to move 3 letters to the left. So if we go Y and we go 1 letter to the left, or 1 letter to the right, that's Z. And then we got to loop back around because we run out of letters. So when we go back to A. So instead of Y, I'll send her A. Instead of Z, I'll send her B. And then on the other side, she knows that our secret number was 3. And so she'll do the opposite. If she sees a D, she'll go to the left by 3. And she'll get it back. This is so cool. Now, this person in the middle, this snooper, won't be able to tell what our message is. because the snooper doesn't know the secret that my mom and I share. I think that's amazing. That is absolutely the coolest thing. All right. So now this is where you get to come in. This is where you get to come in. I want to show you something that I think is really, really cool. All right. So here's what we're going to talk about. Let's switch up. Is everybody okay seeing this? Can everybody see this?
Yes.
Okay. We're going to talk about Stenago. And Stenago is the stenography stegosaurus. And what we're going to talk about is how we can hide things in plain sight. We're going to hide things in plain sight. This is so neat. Okay. We're going to hide one image inside of another. And the one image is going to be one that you see, and the other one is going to be one that you don't. So that when I send a message on the internet, maybe I post a picture on Insta or TikTok or Snapchat, people are going to see a picture, but they're not going to see what I want them to see, because only the other person that I know will know how to get the other image out of that image. But what's cool is you can't tell that I've put another image in there. This is going to be awesome. Okay. So we're going to hide one image inside of another, and then we're going to pull that other hidden image back out again on the other side. And again, the reason why is because we want to keep an image safe. We don't want everyone to see it, but we also want it to broadcast as widely as we can so that the intended audience does see it, right? What if I want to send a message to my mom, but I don't want anyone to know that I've even sent her a message? Well, I just put it in the most obvious spot, which is this big internet thing, TikTok or Instagram or Facebook, and everybody can see the image, but they don't think anything about it. But my mom can see the real image. Okay, so does anybody know who Roy G. Biv is? Can anybody tell me who Roy G. Biv is?
I don't know.
You don't know? Anybody know who Roy G. Biv is? All right, somebody's in the chat. Let's see what they say. Yeah, very good, Mary. These are the colors. They stand for red, orange, yellow, green, blue, indigo, and violet. So those are all the colors. So in our pictures that we use on the computer, how do we make those pictures? How do we make the color that goes into those pictures?
Pixels.
Exactly. We want to color every pixel. Very good, Victor. Well, in each pixel, we get a final color out of it. And we do that with a combination of 3 different colors. So we have red, green, and blue. Every pixel has a little bit of red in it, a little bit of green in it, and a little bit of blue. And so you say, all right, look, I want to mix those 3 together, maybe more red than green, and we get a different color. Maybe more blue than red, we get a different color. But we can make all the colors we want by just mixing in those 3 colors. Okay, so how are we going to do this? Can you tell the difference between these 2 colors?
I don't know. The one on the right seems bigger. It seems like it has more weight, but then the one on the left seems longer or smaller.
Okay, good. Mary said, okay, so which one's washed out, Mary? I can't see it. Yeah, it does, doesn't it? It seems like very similar colors. Yeah, it's amazing. I can't see the difference. And I think, Victor, what you're seeing is maybe an optical illusion, because those should be exactly the same size. They should be exactly the same size.
Wow, it doesn't look like they're exact same size.
I
The
know.
one on the left, the
Yeah.
one on the left looks bigger.
Yeah, it's so weird, isn't it? Yeah, I agree with you. I agree 100%. Okay, well, there is a difference. There's a very, very, very small difference. So here's what we're going to do. We're going to talk about the kind of image that we're going to hide. And we're going to do a very special image. So if we have a color image, we need red, green, and blue in each pixel. But what if we don't need color in our image? What if we just want to do only grayscale? Do we need red, blue, and green? Or can we make it simpler if we don't need color? Can anybody help me out?
So if we don't need color,
If we don't need color, what if I wanted to make that? Yeah, exactly, Mary. That's exactly right. We'll do one of two things. We know that each pixel in here can be one of two things. It can be either light or not light. We can either shine that light on that pixel or not. So does anybody know what the word pixel means, or how we got that term? This is cool. I love this.
I can't remember.
All right. Mary, you have a guess? It does. It means a very small dot. That's exactly what it means. But it actually comes from the term picture element. Picture element. And if you say picture element really fast, you get pixel. And so they started calling them pixels. And that's where the term came from. Isn't that cool? Yeah, exactly. Yeah, I think that's so cool. All right. So let's say we're going to do this. We're going to zoom in on this little piece of the H here. Okay, so we've zoomed in on this little piece of the H, and now we see what we mean, right? This picture element up here is not dark, right? We're shining our light up here. And then this one over here, we're shining our light, and so on. And then here, we're not shining our light. So what we get is this ability to make a grayscale image, and all we need is one little tiny bit of information. We need yes or no. Yes if it's light, no if it's dark, or vice versa. It doesn't really matter. But we only need one little bit of information. But remember, let's go back for a second. How many bits of information did we need for color? We needed a bunch, right? We needed a bunch of different colors for red, a bunch of possibilities for green, a bunch of possibilities for blue. So then we can mix those together. So here's what we're going to do. We're going to say that I'm going to look at this. So if you look on the left, this color here is 180 green, or I'm sorry, 180 red, 57 green, and 102 blue. This one over here, on the other hand, is 181 red, 57 green, and 102 blue. Can you tell the difference? No, not if you're looking at it really fast. And even if you really like dug in, you probably can't see it. So what we're going to do is we're going to say, if the red value is even, then we'll make that in the hidden image we'll make that a black pixel. And if it's odd, then we'll make it a white pixel. So we'll take our original image. We'll put our hidden image logically over top of it. And then anytime I need a black pixel to be hidden in there, I make the red odd by taking the actual red value and going up or down by 1. If there's a white pixel, then I will make it even by going up or down 1 if I need to. And so just by shifting it one little tweak every time, we're not going to change the picture that much, but we've got it there. And Mary, it looks like you have better eyes than I do because you can see these colors. I can't. All right, so let's do it. Let's do this. I'm going to actually show you something here. Does everybody know who this person is? Does everybody know who that is?
Cardi B.
That's right. It's Cardi B, baby. All right. So I think Cardi B is awesome. So she's okay. She's maybe not as awesome as Rihanna, but she's pretty good. So I like Rihanna a lot. All right. So what we're going to do is we're going to send ourselves a message by putting them inside our Cardi B image here. And this is where you come in. You get to tell me the message that you want to send. What message do you want to send? You said any message you want.
Don't forget to take the trash out.
Okay, good. Don't forget. All right, we'll put you in here, Mary, too. We'll do, don't forget to take the trash out because it would make the house smell on Friday, Monday. Okay. That's our message. All right, so we'll save this. Okay, now here's what we're going to do next. I have this program that I wrote, and we're going to run it. Go over here, we're going to run this little program. Now, what I want you to see is right here in this directory over here, we've only got our original image, right? This is Cardi B right here. This is Cardi. And now what I'm going to do is I'm going to run this little program. Oops, hold on. I was hoping that wouldn't happen, but it did. Hold on.
Is it JavaScript?
It is JavaScript. Yes, that's right. So let's see. Let's change this. Sorry. Okay, let's run that again. And look, now we get we get 2 new files. Okay, so here's our encoded. This is the image. This is the image with our secret message hidden inside of it. Can you believe that? This is the original one over here. This is the original. And this is our hidden one. Can you tell the difference? Oh, we're going to get there, Mary. Oh, don't worry. We're going to get there, Mary. I promise.
Not at all.
I can't tell the difference at all. Can you?
I can't.
Yeah, it is literally, this is amazing to me. Okay,
No.
so now let's see what it looks like when we pull that image back out. Let's see what that looks like. So notice I've named the files. This one's the original, and this one is encoded. That means we've encoded our other hidden file in there. So we're going to look for one called decoded. And there it is. Isn't that awesome?
Wow, amazing.
I think that's absolutely amazing.
Totally.
I had so much fun doing this. You have no idea. It's amazing. So we can make any message we want and put it in there. I think it's so much fun. All right. So I've talked a bunch and I've done a bunch, but I want to hear some of the questions that you might have. So before we do that, I want to say, I'm going to give you an example of some of the kinds of careers that computer scientists have. They can be software developers. You can write applications for the internet, for computers, smartphones, tablets, but you can also write it for things that work like that are in the real world. They can be for airplanes or cars. And we've seen a lot of that these days where we need more things to be made. We don't have enough things. Like when I go to Starbucks, they tell me they don't have decaf coffee. And so that's why I get so hyped up like this, because they don't have my decaf and I have to drink regular. But software developers also make, critically, video games. So they can be creative. Software developers are artists. They're artists with their code, but when they're video game developers, they're also artists in the traditional sense. Or you can be a data scientist. We've got all this data that we're generating around the world, and we need people to analyze it and figure out if there's anything in there that we can learn from. Or you can be a cybersecurity officer. You can keep people safe, keep people's data safe, and not just their data, but also their lives. Because if we have people hacking into our hospitals or our power systems, we'd be in big trouble. Victor, you had a question?
Yes. Is there any difference between a software developer and a software engineer?
No, that's a great question. I don't think traditionally, if people say either of those two terms, that there would be any difference.
And would there be a difference between a software developer and a full stack backend web developer?
No, they are just, that's a great question. They are just different kinds of software developers.
Oh, okay.
Yep. That's a great question. All right. So what do I have to do if I want to be a computer scientist? What do I have to study in college? I'm assuming you can't see the meeting chat in the video recording, can you? Because I'm kind of just moving it around. So I hope you can't. So I studied computer science and mathematics, but I want to be very clear that you don't have to study that. Some of the people that I showed you in the beginning, they didn't study computer scientists, and they turned out to be fantastic computer scientists, better than me even. But if you want to take math courses in high school to get you ready for this kind of a thing, I would take as many logic courses as you can. Maybe you have something called discrete mathematics at your high school. I would take that. Or you could take probability and statistics. I think that's a fun course in general because you get to learn what it's like to roll the dice and to take chances and how often you're going to be right. I'm rooting for Iowa tonight in the women's basketball tournament. So I'm up on my statistics. But you could also take linear algebra. This is especially a good one if you want to do anything with graphics. Linear algebra is really important. And of course, calculus. Got to take calculus. But I want to emphasize that the more you learn other fields, the better of a computer scientist you're going to be because you can make analogies. You can think differently. That's what being a computer scientist is all about, thinking differently. And I know that you've heard that before because I bet that the other people who come in and talk to you say the same thing. You've got to think differently to be a scientist. And not just like different than what everybody else, just to be different, just for the sake of being different. But it's because thinking differently is how we solve problems. If we thought the same way that it took to get us into the problems, we wouldn't be able to get out of them. I think you had last time, didn't you have was the physicist last time, the laser physicist last time? Or was it the nuclear physicist?
Nano.
No, that's what it
Yes.
was. Yeah, I wanted to come see that because I was disappointed because I couldn't be there on Friday. So I was out of town with my parents. We were in Florida. So Mary, yes, probability and linear algebra. Those are fantastic courses. If you can take those, please do. Those are fantastic courses. All right. So again, I've talked a lot. So now it's your turn. Any questions? Yes, graphene is awesome, isn't it, Mary? I think graphene is amazing.
I guess for me is that I'm in the career transition thing, and I want to get into software engineering.
Yes.
So and I was surprised to find out that there isn't as much mathematics in software engineering, but it helps.
It does.
It just adds to it.
Yep.
So I'm trying to look into that. So, but I haven't done a lot of math for a long time. So I'm wondering, it's gonna be like I'm trying to figure out visual mathematics to see, because I found a few websites that could probably help me to learn it. So do you have any suggestions for any other
It's funny.
websites?
It's funny. You and Mary both asked the same thing. And I think you and Mary might want to team up because I don't know very many good resources for that. Although I do know some really cool YouTube channels and they do a really good job teaching things. Have you heard of, I think it's 3 Blue, 2 Blue? Let me pull it up here real quick. He's fantastic.
Yeah. Could you put the website in the chat box, William?
Absolutely. Let me just do YouTube math 3 blue, 1 brown. There it is. This is a fantastic channel that they do all of this with math. I watch these all the time. These are so cool. This person does amazing stuff. You can see I just watched this one because it just came out. It's about statistics. So I'll put this one in the chat. And then there's another one. And this professor is very famous on YouTube now, but he used to be a professor at UC here. And I did not realize that right away when I started watching his talks. But I sent him a message and I said, Dr. Bassett, I was watching your video, and for the first time ever, I majored in this in college. And for the first time ever, I understood this concept because you did it. And so I had no idea. I just reached out to him and just sent him a message. It turns out he used to be a teacher in the school where I teach now. And I think that's so cool. So he's really very good. He's really very good. So I recommend both of those. If there's a topic they teach, they're very good at their jobs. So those are 2 good ones. Does that help? Yeah, Mary, they're very cool shows. I could sit and watch that. I can sit and watch those 2 people teach math all day. They make it so fun. So well done. So well done.
Yeah, thank you. Thank you. I was trying to move from one screen to the next.
Yep.
So what are certain ways of how you can approach mathematics in a more of problem solving way, or because as a kid, I was in special ed and and
I think the best thing to do is I think the hardest thing that people have a problem with when they get into those situations, and Mary, I think this is going to go to what you asked too. And I think the hardest thing is for people to keep a sense of fun about solving a problem, because they get very down and they say, I don't know how to do this and I can't figure it out. And, I'm never going to get it. And then they stop having fun with it. You got to keep playing with it. So if I have a difficult problem, what I'm going to do is I'm going to try to make sure I do examples. Okay, so like if you give me this puzzle, what should it look like when it's finished? What are you going to give me? How can I move it around? How can I play with it? How do I get from this step to this step? And then I'm going to try another example and maybe another example. And I'm going to keep trying different approaches. Eventually, a pattern is going to emerge. That's another thing that's really important about computer science, is looking for patterns. And in those patterns, what we're able to see is how we can forget what doesn't matter. We can forget the details, and we can look at a higher level and think about what's important. And that's called abstraction. And that's really important for computer science.
Wow.
Yeah, pictures and maps, Mary, that really helps. I had some students in my office the other day, and they were fretting that they couldn't remember everything. And I said, you have paper and pencil. You don't need to remember everything. You can write it down. So just writing things down. Start by writing what you know. Yeah, draw and write. Draw things that you know. What can you learn from what you know? And then what can you learn from what you just learned? And then it builds on itself. It's so cool. Carmen, do you have any questions? I want to make sure I'm not forgetting you.
I bet you it amazed them that you told them that they could write something down.
Yeah, they were like, I told a student the other day, he said, he was saying something, and I said, he said, I can't, I'm struggling because I don't know how to catalog all this information that I have. And I said, there's a group on campus that specializes in that. And he said, what is it? And I said, the library. And he said, what do you mean? I said, that's what librarians do all day. Go ask them to help you. He came back 15 minutes later. He's like, oh my gosh, they're going to help me. Libraries. It's amazing.
Yeah, pen and paper.
Yeah.
If it doesn't involve the phone company, they wouldn't know, right?
Exactly. Right. So when I was talking about epidemiology, the virus spreading, how do scientists track it with computer science and math? That's a great question. So one of the ways that we do it, well, there's two different ways. That graph that we had here, I'll go back and I'll share my screen again. That graph we had on the right. Let's see. Drive. Let me just open this back up before I share my screen again. Okay, slideshow, share. Okay. So this graph on the right, this graph over here, this is how we do this. We have two different kinds of things going on here. This thing on the right is actual data. That's data we collect by talking to people, by asking doctors. Each hospital tracks this information, and then they submit it to a central repository. And there's a computer scientist who's responsible for nothing but receiving the data reports from the hospitals, cataloging them, and then giving to other scientists, giving that data to other scientists. And on the left, what we did was we try to think about the real world. We try to think about the real world and the biology and figure out, okay, how many details about the real world matter to how this virus spreads? And there's really only a few. How close people are to one another. What's the likelihood that they will come within that distance where viruses can spread? How often do we see other people? How many people are in a certain spot at the same time? And we can use that. And over here on the left, what we're doing is modeling. We're making our own world in the computer that we think mirrors what it's like in real life, but it's obviously much more simple. And the idea is to make something as simple as possible that looks and acts like the real world. Because the harder it is to model, the more complicated the model, the harder it is to get a good result. And the idea, the goal of this is to be able to predict something, because this graph on the right, we only know once it's happened. We can't help people prepare once it's already happened. But if we do over here, we can help people prepare, because on day 1, we can say at day 17, we're going to be in a world of hurt. So we better be careful. But over here, we only know that in July, we were in a world of hurt in May. That doesn't help. So they kind of feed in on each other. We take the real data and try to make a model. And then we use the model to help us figure out what's going to happen next. And then we take what actually happened next, put it back in here, make a correction. This is how we can decide and determine how things are going with the climate. This is exactly what we do. The more data we have, the better our models. The data tells us what the climate was like yesterday, or 10 days ago, or a year ago. It's not going to help us with whether or not, we need to cut down on carbon emissions tomorrow or the next day. So what do we need? We need a model that's going to tell us how do we make this better in the future? So that's the answer to that. Great question.
I did have a question about how did you get that projection? And you took it from the one from the right, and then the information you got from the right, then you were able to make a model and a projection for the future.
The model is our understanding of the way people work in the world, how they move around physically. So we didn't have any data ahead of time for that model. We just took the basic facts of there are 5,000 people in this square mile. That means that they're likely, if they move around randomly during the day, that means they're going to come in contact with 15 other people every day, let's say. And we know that if for every 12 people that I come in contact with, I give it to one other person. And then I simulate that. I move people around randomly in my little world, and I see how often they bump into each other. And every time I bump in, and every 12th person I bump into, I spread the virus. And then I get how many people, then I say, I'm going to stop that simulation every minute or 2 minutes or 3 minutes. And I'm going to say, how many people have it right now? How many people have it right now? And then I'm going to make that graph. But I don't know necessarily that it's 1 in every 12 people that I run into, I give it to. So that's where we take the data that we actually see and put it back in the model. We can make that, oh, maybe it's 11 and a half instead of 12, or maybe it's 13 instead of 11 and a half.
And that's basically on an XYZ graph.
Right. So the graph I was showing you was on an XY, it was just 2-dimensional, because all we're measuring there is how many people have it in the population. That's up and down. But in our model, we're in a volume, right? We're in a 3-dimensional space where we move around.
Mm-hmm. That's like with the plane, you were showing the plane before.
Exactly. That's right.
Yeah. I really like that
Yeah.
one.
Yeah.
I guess that one would be a little bit more difficult to explain than the one that you're showing previous.
No, not at all. Not at all. It's just another point. It's just another data point. That's all.
It's a data point.
Yeah. Mm-hmm. Yeah.
Could you expand on the data points?
Sure. That's what we were talking about when we had the data that we get from the hospitals and other things like that, or whatever we're trying to model, we need data that actually happened. So if it's people in the air, exactly, Mary, it's like new information. It's like if we're talking about airplanes and things in the air, we need maybe the government to tell us where the planes are at any given time. Or if we're talking about how people move from city to city, I'm going to need the Census Bureau to tell me where people go. That's a data point. So data point is, let's say we're modeling how the population changes. The data point is on January 1st, 1972, there were this many people living in Southern California. Exactly. That's exactly right, Mary, like a starting point. And then I can play it forward. Yeah, very good.
Okay.
Well, I know you all have spring break to get to, so I don't want to take too much of your time. Thank you for having me. And everyone, I had a great time. You all have very easy access to me. I promise. If you would like to email me and ask me any questions, I would love to have you do that. And I'm already excited about the next time that I get to come back.
Oh yeah, you're like a continuous rotation here.
I can't wait.
You
Can't
need
wait to
to,
get.
and you actually need to take some time and just call me. I'm up all night. I don't go to
Okay.
bed, so I'm
Okay.
like a night owl. So
You're like me then.
I know that you're a few hours away, but I'm up. Until I only like get a few hours sleep every day for some.
Okay.
Because you ever been while you're sleeping, your mind just keep going while you even sleep. So that's me.
Yeah,
But I'm gonna cut this recording.